meeting. Scotty. Everybody heard that. Okay. Turn that down. They ask us, what do you want in your students? And we are looking for things like, oh, we want them to know how to program in C#, or we want them to know this or know that. We're asking employers in the area, what do you want? And we are expecting tools. That is not what they want. They want those ambiguous things called soft skills. Do you play well with others? Can you communicate? And so on and so forth. Several years ago, I had a student who was really bright, could not land a job anywhere. He was really timid and didn't know how to put himself out there, didn't know how to sell a skill set. So I told him to take a drama class, learn how to get outside yourself. It's okay to pretend. Okay. Half of teaching is pretending. Don't let anybody tell you otherwise. Okay. This is why I'm stressing portfolio, because the employers in the area say we can teach the tech. But what they really want is, are you going to fit with the team? That was the #1 criteria when I was at Foster's and at Tab and the other companies I've worked for over the years. Will you fit? Step 1. Are you trainable? Step 2. And that's where a lot with an attitude with, I don't know, I would like to learn more, is very helpful. Right? But this fellow starts off and says, how do you write an assembler from scratch or doing this? I want to learn this by going high level. And I'll put these links on the website so you can go look at this. And he sit there and says, no means an expert. And he explains what he did. He blogs it. And then he puts together this stack parameter. Whoops. And he's explaining the stack via 8.8. Isn't that a great sound, folks? So, I don't know, the doctor I go to, they implemented a new software system. They call you, they text you, they email you. Make sure you're coming to the appointment. Go in for allergy shots once a month. Come on, I know the routine. Even now, good freeze. Okay. Anyway, so here's it grows downwards. I'm going to come back to this in a second. Okay. So this link, he's walking through the stack and he says, hey, we're going to print hello to the screen by using the stack. How do we do that? How do we increment and decrement the stack to put stuff on and to pull stuff off? Okay. And basically, here's our memory location, and then we have to use the offsets, okay, to be able to put it in and take it out. Okay. Notice it starts high and decrements down to H. And then when we pass it, okay, now to pull it off, we take H and move it back up. Okay, this is really simple. I was thinking we might do this in class tonight, but I want to get through some other things first. And if we have time, we'll come back and visit this. Because maybe on your machine, if we bring it up, you'll be able to copy and paste it from the site into your editor. But on the Windows machine up here, I'm having a dickens of a time. You know, I'm getting real close to just having a boot drive of Linux on this machine and just forget about all the Windows crap. Because I can get Zoom to work. Okay. All right. So, and he goes on and he goes into much deeper detail. But I thought this was really cool. He explains it, and then he's building on it as you grow. Okay. And he's showing you what he does. And he's always using main here because he's not linking things with GCC. So he's not using the underscore start. Okay. And he's using the x86. Okay. So I'll save that off there so don't forget it. And then what I want to do is show you this. This, folks, is the deep end of the pool. The person that wrote this book travels the globe teaching how to do reverse engineering and forensics on code, specifically ARM, because ARM is a huge attack vector right now. Why? You can get 100 Raspberry Pis and set up your whole shop floor enterprise. So do you think a default Raspberry Pi could be hacked? Oh, yeah. Well, how would you find it? How do you know? Well, this book goes into how, and she's got two versions. It's a Blue Fox, which is the defense blue team, and Red Fox, which is currently writing, red team. So if you get into security, red teams are the bad guys and blue teams are the good guys, and they defend. And oftentimes companies will hire red teams unbeknownst to the internal team. And then they get hacked on purpose with a fee. And then they write up a report of what you did, what you didn't do, so on. It's quite the undertaking. And this book is very thick. It goes on forever. But on her website, she runs a class and she talks about the assembler and ARM family versus the ARM architecture, writing an assembler, how to use it. She does everything we've been doing up to this point, but there was a part in here. Basics tutorial. This is where I learned about GEF. I was reading through her book, and she uses GEF when she does forensics for high-end stuff. Okay. And if I can remember where I was, the links at the end are great. So it's called Azera, AZERIA-labs. And there's a lot of video or things. And here's something I did not know about ARM. We've talked about Big Indian, Little Indian, how it's stored. I did not know that the ARM chip has a switch that you could flip and make it Big Indian and Little Indian. I did not know that. That is slick. Okay. So as we move on, it shows you which the registers are for, how they're used. Does it look vaguely familiar? Of course it does, because it's using the gas assembler, which we've been playing with. Now, this is not the actual command at the binary little machine code level that doesn't move. That's going to be different based on the hardware you're on. Okay, you all get that now. Okay. Okay. And you can see how things are all nice and pretty colored. Then she explains how she does it and then goes into the, okay. This is actually really well done. I want to spend some more time going through this. This also led me down I'm going to skip over that, load and store. This is the load and how it moves. We've done that before. Disassemble, we've done that. Have we or haven't we? We use the disassemble command in GDB?
I think we did.
Yeah, I know that it's available. We just forget it. Everything in GEF, because I saw that and I'm going, huh, what's this GEF thing? And then that's what, because I'm always learning too. You know, this stuff is changing. And the past 3 weeks, the security blogs that I've been following are just lighting up. I mean, the exploits that are happening at deep levels, the 0-day exploits they're hitting everything with, is just going crazy. And then there's this other argument, open source. There are companies that are pulling open source out of open source, so they can actually help defend the source code that they quote own, unquote. I don't know if the days of open source are numbered, but when you go, if you load Node.js and the NPM package manager, if you load up a very simple Node app, it loads maybe 30 to 50 extra packages right off GitHub. Are those all secure and vetted? Safe bet they're not. This is what we call a supply chain attack. This is, and this website is, okay, now that we got corrupted, how did it happen? What do we do to defend against it? And what's the code? What's the code doing so we can defend against it? Reverse engineering. Okay. And it shows you, here's an abstract illustration. So I picked this site because this was the only site I found that actually kind of explains what's actually happening and how it moves. Here's what's happening in memory, and then what's going on in the registers. And when you move things back and forth, it kind of makes things a little easier to wrap your brain around. And there's one in here I want to show you. I think it's load store multiple. That's not what I want. That one. Let's go to number 7. It's right at the AVM stack. Okay. They're doing the push and pop. This is what I wanted to bring out here. There is a full ascending stack. There's a full descending stack. There's an empty ascending and an empty descending. What does this mean? Well, it's just how you put stuff on the stack, either from the bottom up to the top down, or you start from 0. Okay. This may not need to know. If you're going to be a web dev, probably not. If you're going to be a financial guy, probably not. If you're going to do device drivers, then again, maybe just based on the chip you're using. But if you're doing forensics and you're trying to unravel the code that just wiped out your enterprise, yeah, you want to know this.
Are those different technical implementations of a stack, or are they just different visualizations of the stack?
Technical implementations.
Okay.
They are, you can actually, when the chip is designed, that's the technical way they build it. And in that vein, if you want to build your own CPU, you can now do this today. Pick a RISC-V processor, choose 10 cores. You write the HDL, you send it to these companies, and they put all these custom chips on. I think you have to buy a minimum of 100, and it's like $10 a chip. And you can design your own chip from the ground up. Wouldn't that be cool? A lot of work, yeah. But yeah, talk about a portfolio builder. Yeah, I built a CPU. Okay. So that's that there. Okay. And then we have the frame pointer and the stack frame. Okay. Now this goes back. Oh, nightmare. A stack-based machine. And I worked on something called Universe, and it was an implementation of the PIC database, which was a non-normalized first form. And it was all a stack-based computer, the whole thing. You actually wrote in a flavor of BASIC. It was unique to itself, but it dealt with variable field lengths. And it had this thing called multi-valued multi-values. Think of an array to an array, and they're connected like this. So you have more than one array, and you put your data in the arrays across this way. So when you pull the key, it goes and actually pulls it out. It's very fast if you knew the key, but the software tired out and people didn't update it and so on. But when we had problems with the code, we had to dig around in the frames and the stacks to see what went wrong with the interpreter. Yeah, 10 years of my career worth nothing. Okay. So you want to put your time into things that the market is taking. The technical best doesn't always win. Just look at all of the technology IBM had. Okay. All right. Let's see if this one. Okay, here we go. Here's another one. And it's walking through this. I like these animations. You can tell she spent a lot of time training people how to do this. I think she's based in Germany, but her website's based out of Iceland. You know, that's interesting. With cheapnames.com, where they got the domain name. So you can look all that stuff up when you find a domain name. Just go to who owns it. And they do a GOIP to find out where it's located. I think this is pretty cool. Kind of explaining some interesting things. And then there. Okay, now bring that over here. All right. Now let's go back to our little world and play around with the GIF a little bit. And I'll give you some ideas. Let's see, I need to go to so many screens open. Yeah, here we go. All right. in our, I want that one. I think it's this one, chapter 6. To upper. Yeah, we'll use that one. Going chapter 5 with the metal up. Okay. If I asked you, say, here is your C program, convert it to assembler, we'd all use the -S, right? Here's the constraint. You can't use GCC to link it. What would you have to do to your assembler code to replace stdio? Yeah. The stdio handles the system calls. So you don't have to worry about, how do I open a file? How do I close a file? How do I write to a file? That's what this is doing right here. They're setting up the system call numbers to do certain things. Okay. This is what we'll play with tonight, and we're going to put it in our new fancy debugger and watch what's going on. Okay. And I think what I will be doing for a final in this class, if you want to call it that, is a final project. Well, you'll be taking what we've learned and kind of redoing most of what we've already done, but into a single project and documenting it and trying to make it look like something you're going to put on GitHub saying, this is how I learned it. Because if nothing else, you can use it for a portfolio piece. Okay. That's really the goal. You know, you come to school, you get your grade, but your grade doesn't always get you the job, does it? So what does? Well, knowing people, that helps. And knowing what's really required of you once you're out there, because you don't get a lot of that in school. You know, I don't know if they still tell you in resumes, but the resume objective, all that needs to be is the job description that you're going for. It does not need to be seeking some great lofty ideal based on blah, working with an advanced company, blah, blah, blah. Nobody cares. The first person reading your resume is going to be a computer program. And it wants to know if your objective is the job you put the resume in for. So make it hit. Okay. I don't know if they teach you that in the resume writing here or not. Anybody taking their class? I know a few years ago they had this objective, and it was, you need to put your personal mission statement here. And that's great, but when you're sending out 1,000 resumes, it's not going to help you. I read a fun thing how one fellow is using GitHub to generate his resumes. So he's got this is what I used to do, kind of, nothing fancy like that, but I had a master resume that had all the gnarly detail of everything I'd ever done. It was like a book. And then when a job came forward, I would grab paragraphs that I needed for that and slant my resume for that job. It worked. Okay. And that's what this guy's doing with GitHub. So here's our code. We're going to play with this. We're going to type it in. We're going to make it work. Okay. So this is in programming from the ground up. And it is, you can just go to GitHub too, because it's all there, I think. There's another one I want to do in this category. It's a typewriter type program where you take one character and it puts it on the screen. All right. Let's see if I can find it website. Mr. Fumar, Marfu. Boomer. That's it. Yeah, there it is. GitHub. There's code. So go ahead and rip it off. You can do this any number of ways. You can download the code. You can do GitHub. You can click on raw and it just comes up in a raw text format. And then you do Control A, Control C, and now it's in your cut buffer. And now you can just paste it into your video, or not your video, your editor. Maybe. I've been having trouble with this. I have updated the Jeremy lab, and there was a patch release for the terminal. So let me know if you still have problems with the terminal, or if you're just using SSH, you're not seeing it. Yeah. Because once you move away and you start using SSH, the speed is so much faster, you kind of get hooked on it. Yeah. Chapter 5. Okay. Yeah, everybody got it? Now, compile it or assemble it, we should say. And then remember what we needed to do? Is this NASM or gas?
Yes.
Right. So we'll be using NASM or AS?
Yes.
Great. So I'm going to copy to upper S to upper underscore org. So I have the original copy. Yeah. Back here. Oh, it was on that, guys. Let me see if I can find it. Oh, bummer. Too many things open. This one. So on this fellow that learned it or is teaching himself assembler from the ground up, there is a command line that I have not shown you. What's that funny little and in there? Amper. You know how we separate it with two commands?
Yeah.
This joins them together. So you can do it this way too. Okay, so you can say, in our case, it'll be I386 because this is NASM, but you can still use this, the and amper. So it says assemble it and link it. That's kind of what it's doing. Okay, rather than assemble, stop, start over, link. Okay, so it creates kind of a process chain. So, what do you want? AS dash that. Well, I want the G in there. 32 to upper. Amper. And then I want LB. And then I need the library style. Elf. Should write all these different command lines down, going between NASM and ASM and gas and so on and so forth. Because this is the stuff you forget. I know I do. Oops. All right. Now we get to have some fun. Why didn't it work? First of all, we're just ripping off the code and it says it's converting things to upper to lower, okay, or to upper. But what is it converting? Well, I see some Linux calls here. And file descriptors. I'm looking for something that says, hey, where is this going to do its thing? What does it take a file name from the command line? Does it open a file? What's it actually doing? And this is how he's doing it. So what this is saying? Okay. What do they mean?
Well, I assume it just put the file name you want to turn into uppercase, and then the other one's the name of the uppercase file.
Right. The file that doesn't exist is this one.
Yeah.
The file that does exist is this one. So we will use just another fun thing. We'll call it, I don't know, brown fox. Yeah. So basically I have 11 lines and it should convert it all to uppercase. Magic. It worked. Slick. Now, what we'll be doing is playing with GIF and looking at this in the debugger. Okay. So I'll leave that up for the moment. You can kind of see this. I know it's a little confusing to bounce between NASM and gas and back again, but I think it's a good thing because that way your brain doesn't get stuck on one and then you can move back and forth better. Are we ready? Ready to play? So once we get this typed in, I could make you type it by hand, right? Then we'll spend another hour debugging our trouble. Why bother? What we'll do is we'll use the debugger to go through and look at the code and kind of explain what the code is actually doing. Okay. And while we were doing this, I want you to think of a program where you get a character and you print a character. That's it. It's not going to save it to a disk. It's just going to, whatever the user keys in, shows up on the screen until the user hits, I don't know, 7, and then it exits. Okay. All right. Or whatever letter you want to use. The any key. Okay. So think about that as we're walking through this, because that's where we'll be going next. And how are we going to do that? Okay. Whoops. GDB. Then GEF. Okay, so it's there. Up. Reading symbols from it says brown fox is not a core down file not recognized. Okay. Well, that's interesting. Let's see what happens here because it thinks it's a core down. Well, let's see if it behaves itself anyway. Now, we're going to get some errors, but using GEF, you can begin to see here's some environment variables of where we are on the system, what shell is being used, and term editor. Where is it pulling this from? From the program? No. When you log in to your terminal session, you get all these things set for you. These are called environment variables. We kind of talked about these a little bit. Where what happened to my bash level? I created it and I did a bash and it disappeared. cobwebs. It was a great Halloween. You forgot all your passwords. Okay. Yeah, I'll do a quick review. If I say X is, well, I'll say set ENVID equal to, I don't know, hello. And if I echo vaguely familiar where we did this, kind of a, yeah. This is what that is. So if I echo dollar $shell, it's showing me that, so this is coming from my running environment where the code is sitting, okay? It's heap, shall we say. Okay. Terminals, and it shows you right where you are, right there. And it shows me I'm right here. And then I can type in step and see how it moves. Step again. And now I can also say, okay, I want to inspect EAX here. How did we do that? How do we look at a register?
I space R.
All right. So it hasn't been set yet. Now let's inspect it. That got changed to 5. Now what's 5? Oh, I don't remember what 5 was. Go back to our source code, and at the top, they have all the definitions. So I would open up another terminal window here. And you can see this opens a file. It's making sense. We still want to see how this behaves. So when we open a file in the editor, we just type in VI space file name. But there's a few more things going on than just file open. Okay. And we'll see what happens, what actually happens when we do this. Okay. Notice it sets the permissions for us. Okay. I think we talked about permissions a little bit in here. So you've had the Linux class a lot. And then sys open. Now it's moving it or to get our next argument. And then this next one is it's going to create the file. Okay. And I want to see which that one is. Store the file descriptor. But in our case, it's not there. I'm going to have to look up how to get the flags to pass. So, yes, or CGB. Okay. And let's see. Location to read into. I don't, because I didn't get the. Oh well. See how big the buffer is. EDX. That's how big that is. Check for end of file. Now it's going to close the file that it opened. It'll move to flows to EAX, which is going to be 6. And sure enough. So in order for us to open a file, we have to open it and write to it and read it and then close it. Okay, so there are different system calls for each one as we move things into it. Yeah. And here it's using this call and boom, exits normally. Oops, no register now because it's closed. Okay. And as we scroll backwards, we can see how the stack is being used and what gets moved into and out of the stack. Now, why would we need a stack to keep some of this information? Close this to get rid of that funny little thing. There. We kind of need, when we run this, whoops. We'll call it up to. So when I run this, it's going to open Brown Fox, read one character, check, and then convert it upcase. We know it works, but when we're in the debugger, all this information is tied to my current process ID. So I have my bash shell, and this spawns a process, and it does its thing, it finishes off, and then it returns me to the shell prompt, right? So when I do that, boom, I'm back to my shell prompt. But what happened was it opened a file, read everything from the file, spit it out, closed it, exited. Okay. So where was that? Well, that was in our stack space that was allocated for this particular program. So if I ran another program, it would use either the same stack space or different, but when you log in, based on how your machine is set up, there's a limit to how much memory you can take. It's actually defined, and the default is pretty generous for how much memory you can have allocated to you for processes. Okay, and this is pretty true for Windows too. If you do run out of memory, it uses swap. How many have deleted pagefile.sys? Yeah, no. The pagefile.sys in your root directory on Windows is a giant swap space. So when you're loading, and you've got a 16 gigabyte machine, and you're loading 60 gigabyte of data, well, it's got where's it all going to go? Well, the data you're working on is in RAM. The data that you're not working on is in pagefile.sys. And then as you work through your program, your Excel spreadsheet or whatever it is, it moves that around, and all of a sudden your program pauses. It just sits there as it's swapping out of disk into RAM, taking what's in RAM, putting it into disk. This is why you can get this thrashing on your hard drive when you don't have your swap space set up right. Not so much anymore. Look, everything's in RAM. I've got a machine that's got, well, most of the machines I work on hardly ever touch swap space anymore. They will, in the case of having a bunch of virtual machines. If I've got too many virtual machines and not enough memory, one of those virtual machines that quote is running will get swapped, and it basically pauses until the rest of them do their thing, and then they go on forward. Okay. All right. You want another homework assignment, huh? I have one I've been working on, and uh hold on a second. I can do it for you. Hmm. So lab 7 is the next one. Let me look at that one. Refresh my memory what's on it. And yes, I promise to get the grading done. I think it's a tradition in our department here to wait till the last week to get all the programming updated. It was that way when I was here in the 80s. You ever gonna grade my homework? Oh, yeah, eventually, 80s, 90s. So basically what we did is pretty simple. Homework 7, where if maybe you're done with it, I don't know, is create a new folder. You're taking 2 working programs, creating function headers, passing the same number to the same functions, and you're changing the header names. Okay. The H.H's, and one of the questions is, can you put all your .c functions or all your .h declarations into one .h file? You can do that. Just watch out for typos. Okay. And then you use your first name and you play with it, and then see how the name changes the output or not. Document your understanding. That's pretty straightforward. Okay. And the questions are, now the program I gave you is a Fibonacci in C and a factorial in C. And then one of the questions is convert the fib and the fact C into S files, recompiling with GCC. So you can use AF still, but you have to use GCC to link, or you'll get screaming failures. So you're going to walk out of this classroom with some pretty kind of weird information. You're going, oh yeah, if this is generated by GCC, I have to use GCC to link it. That in itself could save you 100 hours of headache. Okay. All right. And does it work the same? And use the GCC-V flag to explain it, and then just explain what you're doing. Okay. So that's 7. When did I make that one due? Thursday? Yeah, November 9. Okay, November 9. So our next assignment is, I will give you some code that kind of works around the edges. And what I want you to do is we're going to write assembler. Your choice. You can use NASM or GAS. And it's basically going to take one key input and print it to the screen until you come to a character. And then whatever character, let's see. I think we should make this a little easier. You put a character on the screen or type in a character, prints on the screen, exit. That's all it's going to do. Any character to the screen, exit. In assembly. Okay, that's what we'll be going next. And in your metal up and this one. And I did put, there's a new one in files. I just loaded it up today. You will probably never need it, but it's this one. If you are interested in building devices and logic gates and building things from chips, this would be ideal because it will actually show you how it all puts together, how the clock works and how you move things through the system. They actually use a computer where you load switches. I'm going to put in my hexadecimal A, load, and then tell it to do something. So I find it interesting because I came from there. It might be too old and too low level for anything you're interested in. A lot of you are taking this just because you have to. I get that. I just want to survive. I want to get out of here. I get that too. Okay. I remember I was in school 35 years. I know all the tricks. So, and my recommendation to you is, I don't care if you use GPT. I don't care if you cheat. It may help you get the job, but you won't be able to keep it. That's all I got to say about that. Okay. So if you know how to use the tools and you can explain what's going on and you can explain why it's helpful and how it was helpful, sure. But like any tool, you got to know how to use it. When students would get programs to work, and I said, well, what did you do? Well, I found this code online and I pasted it in and it worked. I said, do you know what it really does? No. What's the likelihood that person's going to make it through probation? Yeah, because I got it working. What'd you do? Oh, I copied it from the internet. I stole it from Stack Exchange. I'm talking to a programmer in China and I'm paying $20, like the guy that actually outsourced his job, the guy at Facebook. You hear that story? He worked at Facebook. He was getting $120,000, $160,000 a year. And he outsourced his job to somebody in China. This was way before pre-COVID. It was about 3 years before pre-COVID for about $20,000. Getting along fine. And security comes. Why is there a Chinese IP address logging in with your credentials at odd hours of the night? And then the security team did what security teams do. They set up proxy logs and found out what he spent his time doing that 8 hours a day. You watched a lot of cat videos. And he sent email back and forth to his Chinese counterpart. Needless to say, he was set free to pursue other alternatives. Okay. Now, there is this raving debate of, hey, I can work 2 full-time jobs online, being remote. Sure, go for it. But you probably won't advance very far in either one of those because you'll always be running at 60, 70%, which is great if you know how to run at 100%. But if you only know how to run at 60%, that means you're going to run like 30% in each job and you'll get fired from both. Okay. So, and things like that are getting tougher and tougher to figure out because the logging and the amount of information their employers are collecting on their users is almost as bad as what Google and Facebook collect on you. Not quite, but it's getting there. Okay. So on that note, feel free to use any reference that you want to, and you can use NASM or GAS. And we'll start with that. And I want to see if where you are, say like next time we meet, as if you're all done with it, cool. That's great. Then let's make it go until a special characters hit and then prints it to the screen. Okay. I know you can find sample code. That's fine. If you find sample code, document the snot out of it and explain it, run it through the debugger so you can understand it. Because the next thing is you can send it to the printer or you can send it to a modem. Because I do need to show you this only because you remember the phone, my phone going off? Oops, I didn't spell that right. In 1981, Dennis Hayes created the smart modem. And you're going, why do I care? Every single cell phone today still uses that command set to make a phone call. If you've never drilled down into the guts of your cell phone, you don't know that. But that's how it makes the connection to the wireless. It's using a ATDT command line set. So what's old is old. Yeah, I agree. But it doesn't mean it's not used. It's just buried so far down and it works so well. It just works and you don't even think about it. Kind of like when I showed you my spark plug, right? Or did I show you? Beginning?
So.
No. I know it. Well, most of you know what this is. Some of you. Yeah. How many have ever changed one? Yeah. How many know where they are? Okay. How many know what they're used for? Three out of all of you. Four if you include me. You get in the car, you turn the key and it goes, right? That's what makes the spark to fire the gas to get your piston to go up and down. The thing inside your car that turns the crankshaft, that turns the transmission, that turns your wheels. This is the AT command set in your modem. You don't necessarily have to know that that's there, but there are things that you use every day that you truly don't understand. And that's what happens when you start digging back covers in assembler. Wow, there's more here than I thought. Wow, there's more. And you just keep going and you keep going because it's got like 70 years of evolution. Okay. But yeah, most of you will never have to mess with us. Okay. Or the Hayes command set. I bring that up because what we're doing is kind of the equivalent of using the AT command set and sending individual characters to a modem to make the modem either call or receive a call. Or a fax machine uses all this stuff too. Okay. Nobody uses fax machines anymore. Okay. All right. So I will give you the last 25 minutes of class to play with, look through the books in assembler, look through things, saying, write it in C, make it work, and then start stripping back what system calls are being used. Because you can use the debugger to find out what system calls are being used, and then get rid of stdio and do the syscall thing like we just did in 2-upper. Or it might be easier just to edit 2-upper. Whoops, I don't think I have it in the history of this one. To find out where it writes it, maybe you have it do both. Write to the file, but what about write to screen? What system calls for write to screen? Maybe it's 3 lines. Maybe it's a whole new program. And if you want to leave, you can. I'm not your mother. Oh.